This lecture is entitled Global Warming, Climate Change, and Sustainable Energy. And Sir John Houghton is the laureate of JapanPrize in the category of global change. Sir John, please.
Ladies and gentlemen, it's a great honor for me to receive the JapanPrize, and it's also a great privilege for me to be giving this lecture here to you today. Most of my time over the last 10 or 20 years has been spent on the subject of climate change, but talking about this prize this afternoon gives me the opportunity of looking back further than that to some of the work I did earlier on and some of the way in which the subject of meteorology and climate has advanced over this period. There has been a revolution in our understanding of the Earth's weather and the climate, which has come about very largely because of two technical advances. It was in 1957 that the first Sputnik went up and was launched by the Russians. And in 1960, that was followed quite closely by the first weather-observing satellite, TIROS, by the United States. The era of observation from space had begun. I was a young man then, or comparatively young, and it was a very exciting period because we wondered just what could be done by looking at the Earth from space. Previously, the weather had been just observable over fairly small regions. Now the possibility had arisen of looking at the weather and the climate over the whole world. And it's an integrated system. What happens in the southern hemisphere today affects what happens in Japan tomorrow. So we were able to begin to look at the circulation of the atmosphere on a global basis, and these global continuous observations were something which we were very excited about. The first satellites, of course, were quite small. This shows one of the large satellites that is flying today, one of the largest for Earth observation, launched by the European Space Agency in 2002. You will see also, on the same scale, a Nimbus Satellite, which was one of the satellites which we were using in my laboratory in Oxford. And beside that, you will see a human figure, just to put the whole thing into scale. So although they were small compared with the latest satellites, they nevertheless had very exciting possibilities. And together with Professor Desmond Smith, who was at the University of Reading in those days, I and my group at Oxford began to look at these new possibilities. And we devised ways of deducing the atmosphere's temperature structure by looking at the infrared radiation emitted by the atmosphere from above and received by the satellite. We had some rather clever ideas for doing that, and we were able to work with the American administration, NASA, in building satellite instruments. And the region we were most interested in at that time was the region of the stratosphere, because very interesting things happened there. It was the region where most of the ozone resides, and there were large waves propagating into that part of the atmosphere from down below, but amplified on the way up. This gives you an example of a planetary wave, which we observed very early on in the period of our first satellite experiment. The region which is marked plus was warm. The region which is marked minus was cold. There is 60 degrees Celsius difference between the temperature at that level of about 50 kilometers in this very large planetary wave, which was called a stratospheric sudden warming. And so we were able to study these dramatic disturbances. With the third satellite instrument we built in 1976, we were able to measure the global temperature structure from the surface right up to 90 kilometers in altitude. A cross-section of the atmosphere is shown on this slide, from the surface right up to the top, from the North Pole to the South Pole, from the surface to 90 kilometers, and from two instruments which we had built, we were able to get the total temperature structure in that way over the whole atmosphere. And of course, we have more refined information available today, and this sort of information is used for modern weather forecasting. The second very important technical advance, which has made this revolution in meteorology and climate possible, is that of the growth of computers. Computers are growing at a factor of 10 every 6 years, and have been doing so ever since 1950. It happens to be a straight line. There's no reason why it should be, but this is just the power of the computer industry, about which you know a great deal in Japan. And computers early on enabled us to begin to integrate the equations of motion together with the underlying physics of how things happen in the atmosphere, and to create models which would enable prediction of the weather and the climate to be made. They are probably the most elaborate models, computer models, of any system in the universe which we're able to make. And meteorologists and climatologists are very greedy people. They want the most sophisticated and the most advanced computer which is available. And you have here in Japan the Earth simulator, which is the most powerful computer of that kind available today. And scientists in the Hadley Centre in the UK are very pleased to be using that facility. Just to give you an illustration of the power of that facility, this is not a real picture from space. It is a simulation of a typhoon over Japan with a very high horizontal resolution simulated by that wonderful facility you have at Yokohama. So it's the combination of the simulations of the climate from computers put together with the observations from space which has enabled these enormous advances to occur. My scientific work in the 1960s and 70s was very largely concerned with the physics and dynamics of the stratosphere, where ozone is, as I've explained. But concern developed in those days about the possibility of depleting the ozone layer because of human activities. In particular, we are able to release into the atmosphere, or we do release into the atmosphere, from aerosol cans or by leakage from refrigerators, chlorofluorocarbons, in concentrations of a few parts per billion or even trillion, which get into the stratosphere and destroy the ozone. And because these polluting molecules remain in the atmosphere for a long time, they spread through the whole atmosphere, and this is an example of global pollution. It's pollution which we all contribute to, which doesn't just affect us in our local area, pollution which is emitted in Tokyo, which doesn't just affect Tokyo, it affects the whole world. During the last 2 decades, there have been a second, and even more serious example of global pollution recognized. Through the burning of fossil fuels, coal and oil and gas, human activities are causing the emissions into the atmosphere of the gas carbon dioxide, which leads to warming and hence to climate change. So the science of climate has been brought into very sharp focus, and emphasis has also been given to the technology and to the policy changes which are required to mitigate the impacts. Global pollution demands global solutions. And for the rest of this lecture, I will be particularly addressing this issue. Let me start with a quick summary of the science of global warming. The underlying physics has been known for 200 years. The greenhouse effect, it is called, and solar radiation comes into the atmosphere and warms the surface. It's largely unimpeded in the absence of clouds. But that energy which is absorbed by the surface then has to get away, and it's radiated. Energy is radiated then from the surface in the infrared, and it's heat radiation, thermal radiation. You can feel it, but you cannot see it, of course. And some of that radiation gets out to space, but a great deal of it is absorbed on the way out by greenhouse gases in the atmosphere. Carbon dioxide and methane are two of the most important, and they act as a blanket over the Earth's surface, causing it to be warmer than it would otherwise be. Just like a blanket in bed keeps you warm at night. The top of the blanket is cold, and the bottom of the blanket is warm. A greenhouse works in the same sort of way. The glass in a greenhouse lets through the sunlight, but stops the infrared. Now, since the Industrial Revolution 200 years ago, one of these gases, carbon dioxide, has increased over 30% and is now at a higher concentration in the atmosphere than for millions of years. There is the carbon dioxide concentration over the last 1,000 years, and going up to the year 2100. And if no action is taken to curb these emissions, then the concentration of carbon dioxide this century will rise to 2 or 3 times its present level. Now, the climate record over the last 140 years or so, over the last, of course, many thousands of years, shows a lot of natural variability. Some of that is illustrated in this slide, showing the temperature, the global average temperature of the atmosphere since the year 1860 or so, and going up to the year 2000. I want you to particularly notice the last 30 years or so. The year 1998 was the warmest year on record, and a more striking statistic is that the first 8 months of the year 1998, each of those months was the warmest of those months on record. And when you get 8 ducks in a row, then nature is trying to tell you something. And there's very strong evidence that most of the warming over the last 50 years is due to the increase in the greenhouse gases I've already talked about. Now, over the next 100 years or so, during this century, the global average temperature is projected to rise by between 2 and 6 degrees above its present level. Here are some model calculations done by the Hadley Centre in the UK, but there are many other models in the world that do the same thing. For various assumptions we have various assumptions in these curves here about the emission of carbon dioxide by humans. And this rate of change of climate during the 21st century is greater than the rate of change has been for at least 10,000 years. You may think a few degrees sounds rather little. The temperature in this room has already gone up, I guess, by 2 or 3 degrees since we came into it because of our body heat. But this is the global average temperature I'm talking about. And the difference in global average temperature between the middle of an ice age and the warm periods in between ice ages is only 5 or 6 degrees. So that 2 or 3 degrees, which would be an average from this diagram here, 2 or 3 degrees here, amounts to something like half an ice age in terms of climate change. But talking in terms of global average temperature doesn't really tell us very much about what will really happen. What are the most important impacts of climate change? There are 3 on this slide, and I will deal with each of them in turn. First of all, there's sea level rise. As ocean water warms, it expands. And first of all, you warm the top bit of the ocean, and then over the next few centuries, we will warm the rest of the ocean, but that will take centuries. So there will be a rise in sea level of about 1/2 meter a century going on for many centuries. And this will cause very large problems to people in low-lying parts of the world. In Bangladesh, there are 10 million people below the 1 meter contour. And where do they go in our warmed world? There are many people in southern China. There are many people in the islands of the Indian and the Pacific Oceans. And many regions of the world, many cities in the world are very close to the sea, and there will be big problems in nearly all of them. And then further, there will be impacts from extreme events. Let me just mention one, which is a heat wave in Europe in 2003. All these blue lines represent the average temperature in Switzerland during the months of June, July, and August in various years from 1864 till 2002, covering this range. 2003, that average temperature is out here. That is 5 standard deviations away, if you understand statistics, from the average. And it is very extremely unlikely that that is due to natural variability. The risk of the event is mostly due to the increase in greenhouse gases, and analysis of that event shows that by 2050 it could be an average event. By 2100 it will be a cool year. Now 20,000 people died in that heat wave. So when I speak about global warming as being a weapon of mass destruction, as I have done, and people have said I'm hyping it up, and they don't expect me as a scientist to hype it up, I say I'm not hyping it up. I'm describing it as it is and as it will be. Now, what about water in our warmed world? Water is an extremely important resource. And this is a picture of the River Nile going through the Sudan. I show that because it's a shared river. There are regions here also which are irrigated, the red regions. This is a false color image from space. And it's very good, of course, to see the desert being irrigated and crops being grown. But in our warmer world, there will be more evaporation of water from the surface. There will be more water vapor in the atmosphere. And that, of course, means that there'll be more average rainfall. And indeed, in many parts of the world, we are already measuring and observing more average rainfall, increased rainfall. But there's another very important thing about water vapor in the atmosphere, and that is that when water condenses to form cloud droplets, latent heat is released. If you remember your schoolboy or schoolgirl physics, you will know about latent heat. And that's a lot of energy. It is, in fact, the largest source of energy for the atmosphere's circulation. So our globally warmed world will have a more intense hydrological cycle. And what does that mean? It means that the rainfall will tend to come down in bigger amounts. More intense rainfall will be more common. It also means that some arid areas or semi-arid areas will become drier. And so there will be a tendency to more floods and more droughts. Now, these are the biggest disasters which the world knows. They cause more deaths, more misery, more economic loss than any other disasters we know. That slide gives you some indication of the number of people who died and have been affected over the last 25 years. So more of them and more intense droughts and floods is very bad news for lots of people, especially in vulnerable parts of the world. So what's going to happen this century? How much are they going to increase? It's quite hard with the models to get good data and good predictions about how the droughts and the floods might change. But here is some of the latest work which is coming from climate models today, suggesting that the risk of extreme floods And this is under a world with double carbon dioxide, which means later this century, almost certainly, we will get something like this. The risk of extreme floods in many parts of the world, including the region of the Asian monsoon, will go up by a factor of up to 10. Now, you have floods in Japan, they have floods in China, we have floods in the UK. There have been quite devastating floods in Europe, never mind Africa and Asia. So that is very serious. And the risk of droughts in some dry areas will go up maybe by a factor of 5. Not that there will be more droughts, it seems, but the droughts will be longer. And that makes them even more devastating. If they, instead of lasting a few months, they last a few years, then that is very devastating indeed. So, in our world with increased floods and droughts, there are going to be many environmental refugees. And Norman Myers in Oxford has made an estimate of these and reckons there could be 150 million in the world by the year 2050. And that is probably a very conservative estimate. Now, in addition to these impacts I've mentioned, you will have noticed in the newspapers and in the media a lot of description of what is happening in the Arctic. There you see Greenland in 1992 and in 2005. The red areas are the melt areas in the summer, and that's increased enormously over this period in Greenland. And if the temperature rises much more in Greenland than it is at the moment, Greenland will begin to melt down. This may take hundreds of years, will certainly take hundreds of years. If we really try to do something about global warming, it could take thousands of years, but a complete meltdown of the Greenland ice cap will add 7 meters to the sea level. There's a further concern too, and that is, which is a bit more in the wings of the discussion of climate change, and that is the weakening of the deep ocean circulation, the Gulf Stream, for instance, in the Atlantic, that could change the transport of energy and fresh water in the oceans. And if any of you have seen the film The Day After Tomorrow, you needn't believe all the rapid disaster in that film, but it is actually based on a credible piece of science, which is the fact that there could be big changes in the deep ocean. So let me just summarize what I've said about impacts so far. And while you're looking at that slide, I'll just mention, people will say to me, aren't some of the impacts positive? Isn't it going to be better in some parts of the world? Well, if you live in Siberia and other areas at northern latitudes, the winters will be less cold and the growing seasons will be longer. And providing your house isn't built on the permafrost, if it is, it will fall down, but then you can always build another one. There is also a fertilizing effect of carbon dioxide, which may help some crops to yield more. However, careful studies show that the adverse effects far outweigh the positive ones, and that's why I'm talking so much about the adverse effects that are going to cause us great problems in our adaptation. So how sure are we about the story I've been telling you? Let me mention the work of the Intergovernmental Panel on Climate Change, formed in 1988. I had the privilege of being chairman or co-chairman of the panel's scientific assessment from 1998 to 2002. We got hundreds of scientists from many countries to work with us, and our task was to honestly and objectively distinguish what we know quite well from those areas with large uncertainty. We produced three assessments, 1990, 1995 and 2001. And indeed, all the summaries of our work were agreed by meetings of governmental delegates. IPCC is an intergovernmental body, and there's no assessment on any scientific topic that has been so thoroughly researched and reviewed. But so much so that last year, the academies of science of the 11 richest countries in the world, that's the G8 countries, together with India, China and Brazil, issued a statement endorsing the work of the IPCC and saying that urgent action was required. The academies of science of those countries have never issued any statements on any subject ever before of that kind. So it's an unprecedented thing, and they felt so strongly that the consensus amongst the world's scientists is absolutely unique. Over the period of the last couple of reports, in fact, we found that some of the positive feedbacks of climate change have become stronger, and we become more concerned about the results of our work. Unfortunately, of course, there are large vested interests in the world who have spent tens of millions of dollars in trying to spread misinformation about the climate change issue. And they're still at work, and they are still spreading this misinformation, but we need to be very careful, and the media needs to be very careful to listen to the authoritative voice of the world's scientific community. Now, because of the work of the IPCC in its first report in 1990, the Framework Convention was signed in 1992 at the Earth Summit in Rio de Janeiro. It was signed by President Bush Sr. for the United States, and all countries in the world signed it. It stated that action had to be taken. It said, even though we do not know everything perfectly, we must take action. And that action, of course, has been discussed ever since. And more particularly, the objective of the, I'm sorry, I'm racing ahead of my slides, but that summarizes the work of the IPCC. So I'm talking now about what we can do about global warming. The objective of the convention is to stabilize the greenhouse gases in the atmosphere in order that we stop climate change. Now, what does that mean? We are emitting at the moment about 7 billion tons of carbon as carbon dioxide into the atmosphere as from human activities. If we go on as we are today, emitting more, and some developing parts of the world will emit still more, and then we will be up here by the year 2100, emitting perhaps 15 or 20 billion tons a year. These are figures that come from the World Energy Council, which is the body that joins together the world energy industries. But that World Energy Council also says we could, if we wish, and if we really wanted to, we could follow the green curve. We could start to get our energy from other sources, and we could reduce our emissions to a fraction of their present level before the end of the century. And that would lead to stabilization of carbon dioxide concentration at around 500 parts per million. But they say we have to work very hard to do that. In fact, they show how it could be done, but we have to have the will to do it. Now, the biggest international problem in doing that is illustrated in this slide. These are the carbon dioxide emissions per capita from different countries or groups of countries versus population. 6 billion people in the world, 6,000 million people. And the red areas are from the developed world, the green areas are the developing world. The USA is leading the field with 5.5 tons per capita. And Japan is down here somewhere, or just above Europe, with 2 to 3. And then China is leading the developing world with less than 1. If we're going to cut down our emissions, how do we do it in a way which is both realistic and equitable? And that's the major challenge that the world faces in reducing our emissions and in stopping climate change. Now, the Kyoto Protocol, set up by the Climate Convention, begins that process of reduction. It averages about 5% below 1990 levels by 2012 for those developed countries who have ratified the protocol. It helps to begin to bring these numbers down, but only by a very small amount. Most of them are going up at the moment. The USA in particular is going up rather fast. So it's important, very important for the international community to begin to set up international agreements as to what happens post-Kyoto regarding the sharing out of carbon dioxide emissions between all countries in the world. But for instance, on what level of stabilization should these negotiations focus? Now, I give two examples of stabilization proposals. In 1996, the European Union suggested that the global average temperature should not be allowed to rise more than 2 degrees. The second example comes from Lord John Brown, who is the chief executive of BP, one of the biggest oil companies in the world. He gives lectures on climate change, a bit like I do. And he says we could stabilize and shows how it could be done. He's an energy company after all, and they're very keen to be a real energy company rather than just an oil company. So there are some proposals out there from government and from industry which give us some hope of achievement. But let me remind you again that even if we stabilized at 500 parts per million or a bit less, then we would still be suffering all the disasters and the floods and droughts I talked about earlier. And there is no sign at all at the moment in the world that we're anywhere near the turnaround in the global emissions that are required for stabilization. Now, many economies, of course, are worried about the cost of climate change. Let me just give you an example of a calculation of costs carried out in the UK, not by green groups, not by the Greenpeace or anybody like that, but by Treasury economists, the economists in the Finance Ministry. They were asked to say, what will it cost to reduce carbon emissions in the UK by 60% by the year 2050? That's the result. We might lose 6 months' growth in our economy over 50 years. That is actually very small. It is less than the cost of the Iraq War. So we're not talking of large costs to people's economies. And in fact, as the Treasury people said, this doesn't take account of the opportunities of innovation, which may well come along and make the cost even less. So what sort of action need we take in order to bring about the changes required? We have to be more efficient in our use of energy. There are possibilities of sequestering carbon, and we have to generate energy which doesn't come from fossil fuel emissions. If we take buildings, for example, it is estimated that 60% of the energy which is used in buildings could easily be reduced, or the energy used in buildings could be reduced by 60% with savings in cost. That efficiency can be carried out in the transport sector too. And many of the world's largest companies are beginning to save energy on a large scale and translating that into money with savings of many billions of dollars. And then there are ways of sequestering carbon underground. This is an example in Norway, which has been going on for some years. They are taking carbon dioxide separating it out from gas that comes from underground, and they're pumping the carbon dioxide back again into appropriate rock formations, porous rocks or saline aquifers and so on, in order to get rid of it and to save paying the carbon tax. Norway has a carbon tax, and they actually save money by by sequestering the carbon underground. The same could be carried out in coal-fired power stations by separating out the carbon dioxide and pumping it underground. And that is being proposed. Pilot studies are going on in the United States and in China and elsewhere in the world, and I think we're going to hear a lot more about that over the next few months and years. And then thirdly, there are a lot of non-fossil fuel sources of energy available for development and exploitation. I just want to mention two, actually, from this list in particular, or three perhaps. One is the use of biomass. Another is the use of wave energy. And the third is solar energy. But you will know about all these possibilities. And one of the great things about what we can do about energy to combat climate change, there is no one solution. Many technologists say, oh, the solution is to build nuclear power stations, or the solution is to build lots of windmills. There is no one solution. There are many solutions, and we have to take account of all of them and do the ones that are very best for us, where we are, and best for the communities in which we live. That's a wave energy generator built off the coast of the UK. We have a lot of waves from the Atlantic Ocean, and we could get something like 10% of our electricity from wave generators. I believe you have waves in Japan too, and maybe you could do similar things. I think you are pursuing similar things. But then let me move on to energy from biomass, as it's called, or from waste, maybe. There are large possibilities in growing crops to provide energy, growing crops to provide biofuels to use in transport, or using waste materials, agricultural waste or domestic waste, in order to generate energy. I use the example of Upper Austria, which is a small part of Austria, but they are expecting to get 30% of their total energy from local biomass by 2010. And the benefits of that to their community is large, because the communities, the villages and the towns, make their own energy. They own their own energy. It's very secure. It isn't gas that's packed halfway around the world and may be stopped at any time. It's something they produce, and it helps the rural, local economies very well. And that's a very important thing to think about as we're thinking about energy. And then I happen to be a trustee of the Shell Foundation. The Shell company has set up a large charity to support the provision of sustainable energy for the poorer countries of the world. And we are doing this in various projects in all sorts of countries using material. There are 1 million villages in China that could use rice straw as a source of energy. There must be many in Japan too. But there are, in India, there are these great public toilets where there is sewage that can be used to help to light the town. And in the Philippines, there are mountains of coconut shells from which you can get energy. And I could use many more examples of that sort of thing. And then there is solar energy. I was in India recently, and I saw some solar home systems, small solar arrays with providing light. And if you make them a bit larger, they can provide the other necessities of life, or supposed necessities, like television and fridges. And these should be multiplied in millions for people who have no access to electricity from any other sources. The opportunities for industry, for innovation and development and investment are very large. And Japanese industry, of course, is already leading the world in some of these areas. There is my home in Wales in the UK. Well, part of my home, that is the garage. I live on a hillside in the country, and it is very beautiful. On my roof, I have 4 kilowatts peak of solar cells. And where do the solar cells come from? They are made in Japan. In the garage, we have 2 cars. My wife has one too. They're both made in Japan. I have a Prius, Toyota Prius, which is a wonderful car to have, a hybrid. And my wife has a Daihatsu, a small Daihatsu, which again is very efficient in its use of fuel. So Japan is leading the world in many of the technologies that are required to change the way we do things in the world. Let me congratulate you and encourage you in Japan to do a great deal more, to take the lead in the world in providing what the world needs to change the way we get our energy, and to use modern technology, but to use it appropriately and sensibly and not stupidly. And that's very important. We have to be humble in our use of energy and the way we do things. Two further things, if I may, before I finish. The first is, it's often argued that we can wait and see before action is necessary. That's not a responsible thing to say. Actually, action is urgent for 3 reasons. The first is a scientific reason. We've already committed to a large amount of climate change because of what we've done already. We haven't seen it all yet because the oceans take time to warm up. It will come in 30 to 50 years, by which time, if we're not careful, we'll have got much more commitment. The second reason is an economic one. We're building power stations today we'll be ashamed of in 30 years' time. We'll want to scrap them, but that's very uneconomic. And the third reason is political, and that is that the developing countries in the world, like India and China, want to develop rapidly, but they will follow, not lead. I heard a Chinese speaker recently saying, don't expect us to start. When you in the West, in the rich world, change and reduce your emissions, we will follow, but not the other way around. My wife always reminds me when I talk on this subject that I need to remind individuals of the actions they can take. I guess I've no real need to do that, but when we are purchasing vehicles or appliances, we can choose ones that are fuel efficient. We can ensure our homes are energy efficient. We can use public transportation rather more. And we can also support our leaders in government or industry to give them the confidence to produce the necessary solutions. It was Edmund Burke, a British parliamentarian of 200 years ago, who said, no one made a greater mistake than he who did nothing because he could do so little. And then people often say to me that I'm wasting my time talking about global warming. They say the world will never agree to take the necessary action. Why don't I go and do something else? And I reply I'm optimistic for three reasons. The first is I've experienced the commitment of the world's scientific community. And I've explained that already. Secondly, I believe the necessary technology is available for satisfactory solutions. My third reason is that I believe we have a God-given task of being good stewards of creation and that God will help us with that task. You may ask, why bring God into the discussion? Has not science made it unnecessary to believe in a creator to whom we might be responsible? I don't think so. Science only tells us how things are, but not what they mean or what action we need to take. The founders of the JapanPrize set out to encourage not only the advancement of science and technology, but also the furthering of peace and prosperity for humankind. For our fulfillment as humans, we need not just technical and economic goals, but moral and spiritual ones. And near the top of the list of such goals could be long-term care for our planet and its resources, often described as stewardship. And we in the developed countries have already benefited over many generations from abundant and cheap fossil fuel energy. And the demands on our stewardship take on a special poignancy as we realise that the adverse impacts of climate change fall disproportionately on poorer nations and will exacerbate the divide between the rich and the poor. And the pursuit of this goal of global stewardship could lead to nations and peoples working together more effectively and harmoniously than is possible with most of the other goals on offer. And so I've described to you very briefly an extremely challenging area of science. It asks fundamental questions. Just how predictable is our climate? Or as the scientists would say, is it chaotic? It stretches the capabilities of the latest space and computer technologies. It requires cooperation between scientists from all disciplines and from all nations. And perhaps most important of all, the conclusions of our scientific inquiry are of vital concern to the future of all human beings on the planet. I count myself extremely fortunate to have been part of such an exciting exploration. And so in conclusion, may I encourage many of you younger people in this wonderful country of Japan, with its great tradition of world leadership in innovation and development, to pick up this baton and to run with it. The race is on in earnest, and there's so much to do and to accomplish. Thank you very much.